of an equation at an equilibrium? 0, yeah, because an equilibrium point means constant solution, or equilibrium solution means it's constant, so its slope is 0. True or false, dy dt equals y minus 2 times y plus 1 is autonomous. True. Autonomous means dependent only on y. Nope. Only on autonomous means only on y. Yeah, means it depends only on itself. Y depends, its rate of change depends only on itself. Okay, this equilibrium point that I sketched here, is it a sink, source, or a node? Sink. Everything's sinking into it. All right, so I have a little misnumbered it there because quiz class 6 is actually a quiz. So this is class 7. All right, a phase line is another qualitative tool that we have that we can use to study solutions of an autonomous differential equation. Autonomous means it has only y's on the right-hand side. So remember that the slope field of an autonomous differential equations has slopes that are all the same along a horizontal line. So you studied some of these in our last class activities. So if you look along a horizontal here for a given y value, all the slopes look exactly the same as you look left to right. So there's a lot of redundant information in this picture. You just keep drawing the same thing over and over again. So we can collapse all of this information into a single vertical slice of the slope field. We compress it into a phase line. We mark where dy dt is 0, and then we just put the sign of dy dt on the intervals in between, whether the slopes are positive or negative. All right, so my differential equation is dy dt equals y minus 2 times y plus 1. All right, so where are my equilibrium solutions? -1 and 2, right? Equilibrium solutions happen when the derivative is 0. Y equals 2 and -1. And we can see those in the slope field, although we kind of missed the one at -1 because we didn't plot anything there. But you've got, it does switch from negative to positive, so you can see that. And then at 2 also it switches from negative to positive, and there's a horizontal there too. All right, so if I'm drawing a phase line, draw a line, and I'm going to put in -1 and 2. So those are my equilibrium solutions. Those are places where the slope is 0. And now I'm just going to put in the sign of the slope on either side and in between the equilibrium points. Okay, so if we're bigger than 2, if you replace in dy dt, if you replace y with a number bigger than 2, do you get a positive or a negative? Positive, yeah, like plug in like 10. You end up with 8 times 11, positive number. So we put an up arrow to indicate positive. What if we put in something between -1 and 2? Like 0. It's going to be negative, yeah. So we're going to have -2 times +1. Negative times a positive is negative. So put a down arrow for negative. And then something less than -1, like -10. Get a negative or a positive? Positive, because the y minus 2 term will be negative. The y plus 1 term will also be negative. You multiply them and you get a positive. So up arrow. So this is all of the information in terms of the sign of the slope that we had in this entire slope field, just compressed. Okay. We do lose a little bit of information. It's not quite as accurate as if we use the slope field because you don't know the actual values of the slopes. We only know their signs. But that's enough to give us a good qualitative picture of what the solutions are going to look like. Okay, so I'm going to use that phase line I just drew to sketch solutions to the differential equations. So I'm just going to redraw it real quick. This was positive, negative, positive. Okay. And I should mention the vocabulary that when both arrows are pointing away from the equilibrium point, we call this a source. When both arrows are pointing towards the equilibrium point, we call this a sink. And if one's pointing away and one is pointing towards, we call it a node. Whether it's either direction, like both up or both down, both called a node. All right, so given this little summary of the slopes, I can draw some sketches of the solution to the differential equation. So here's t and y, drawing solutions, y of t, that solve the differential equation. I know I have equilibrium solutions at -1 and 2. Those are horizontal lines at -1 and 2. So I'll draw those in. And then because I know the sign of the slopes, I know what the function is doing, right? If the slope is positive, right? What does that tell you about the function y? If dy dt is positive, then y of t is increasing, right? Remember that from Calc 1? So I know no matter what my initial condition, if it's smaller than -1, the function is going to be increasing from left to right. So pick a random initial condition that's less than -1. Right? By initial condition, I mean at time 0, so on the y-axis there. That function is increasing. So as I move from left to right, it has to always be going up. So this has to go something like this. I don't know exactly what it looks like or where the concavity is and stuff like that, but I know that it's always increasing. And how do I know that it's not going to cross that equilibrium solution at -1? It's an equilibrium solution. Why can't I cross it? Right? What was the last lesson we talked about like a week and a half ago? It was called existence and uniqueness. So one of the consequences of uniqueness is that solutions can't cross, right? Because if two solutions ever share a point, it means that they'd have to be the same solution, right? So it's possible to have two solutions share a point, but not if the partial with respect to y was continuous, right? So if you look back at our equation, it's just a polynomial in y, which means that its partial with respect to y will also be a polynomial and will be continuous. So we have uniqueness in this situation. So that means that we can't cross equilibrium solutions. And for the rest of the course, we're going to have existence and uniqueness pretty much, right? So so if you ever see things crossing, you've done something messed up. All right, so let's pick another initial condition between -1 and 2, like maybe 0, 0. Let's think about what this solution has to do. The sign of the slope in between -1 and 2 is always negative because of this down arrow, right? Which means that my function has to be decreasing, always decreasing. So it's got to look something like this, going down. And it can't cross an equilibrium solution, so it's always decreasing between those two lines. And then if I pick an initial condition bigger than 2, the slope when our initial condition is bigger than 2 is positive, which means that's always increasing from left to right. So it's got to go something like this. So there's a lot of information, right? We can sketch a lot of good information from the phase line without doing a lot of analytical stuff. So this is what we were just talking about. The uniqueness theorem means we can't cross equilibrium solutions. Uniqueness means that solutions can't cross, and we know it's unique because the partial of the right-hand side with respect to y is continuous. All right, equilibrium solutions can be classified as a sink, a source, or a node. And what do these mean? I told you basically already. Sink, when the solutions go towards the equilibrium solution. If I was going to draw this in a ty plane, if here's my equilibrium solution, a sink means that all my solutions are heading towards it, like that. And a source, solutions are heading away from the equilibrium. So here's my equilibrium solution. If solutions are always heading away, so it's like that. And then this is the source. Finally, a node. Either they're both pointing this up or they're both pointing down. Okay, if they're both pointing up, that means they're both increasing. So one is heading towards the equilibrium solution and the other one is heading away. Both pointing down. This one's coming down. This one's going away. All right, so this is a really useful tool, the phase line. It does only apply when you have an autonomous differential equation, which is one small subclass of differential equations, but it's useful nevertheless. So that's it for the demo.